and we're going to be covering gases and the first part of thermochemistry for you guys. So we're going to be pretty much reviewing those concepts, making sure we have a really good understanding, and also doing a lot of practice questions. So if you came to the midterm prep last semester, you're going to actually find that this has a pretty similar flow to it. So we go through theory and practice questions. Okay, so kind of my process for making this, since this is our first time doing weekly tutorials. So when I give you guys the survey, if you have any feedback at all, I'd love to, hear what you guys think, or see if you think of any way that this session could be improved, or maybe you want certain things to be focused on next time. Just let me know, and I'm like so happy to make those changes. But pretty much what the game plan is that so what I did up to this point was I went through past midterms, and I started making the midterm prep booklet based on those. And I made sure that in that midterm prep booklet for Chem 1302, there is, it's super tailored to your midterm. So there's a whole bunch of questions that you're likely to see on your midterm. But then for this tutorial session, what I did was I left in the same theory. So we're still going to be able to review all those concepts, and I just changed all those questions. So if you come to the tutorials and the midterm prep, you're still going to benefit because there's different questions. These sessions are really going to be focused again on understanding concepts. And if I found like a question was super, super hard on the midterm, then I inserted another one like that here, so we can kind of work through that as well. So that's kind of what I was thinking for tutorials. And if we're introducing a new equation, I sometimes put like easier problems just to make sure that everyone understands that concept. So yeah, let me know what you guys think and we can get started. Okay, so we're going to start by going over gases. And the first thing that we'll just touch on is the ideal gas law. So by now we've probably seen this equation a bunch. It's PV is equal to nRT. Well, I just realized I didn't even introduce myself, so I don't know what's happening today. So my name's Avneet, in case you guys don't know. I have a lot of experience with many different exam prep courses, and this booklet, again, has been specifically made for Chem 1302 at Western, and I actually went to Western too, so I'm a Western grad. Yeah, I think Western's an awesome school, and I was actually thinking how excited I am for you guys to finally be able to experience the campus, hopefully next year, but I'm really you're going to love it. I really enjoyed my experience at Western. So yeah, now I'm teaching a lot for exam prep courses, and also I do a lot of MCAT prep too. Okay, so back to gases, we have the ideal gas law equation here. The P is pressure. We can use different units of pressure in this equation, but it's most typically going to be in kilopascals or ATM. So we'll see those two units being used in this equation, and we want to make sure we're paying attention to those units, because the units that we use for pressure determine the units that we want to use for R. So you'll notice that for R, there's two different values you can use. The 8.314 value is if you're using a pressure in kilopascals. That's for when the pressure is in kilopascals. And the 0.082 value we'll use that if we use a pressure in ATM. Okay, V is just your volume, that's in liters, and N is your number of moles. And then finally, temperature is always going to be in Kelvin. You'll see that a lot in chemistry. Okay, so if you are given a temperature in degrees Celsius, you know that we have to add 273, and that's going to give you a temperature in Kelvin. Okay, this is just a reminder of how the different units of pressure are related in case we need to convert something into ATM or into kilopascals. So 101,300 pascals, you just divide that by 1,000 to get the answer in kilopascals, and that's equal to 1 bar, which is also equal to 1 ATM. And then the other numbers or values that you might see is that's also equal to 760 millimeters of mercury, and that's equal to 760 torr. So there's so many different units of pressure, but again, the ones we want to be most familiar with are kilopascals and ATM, and we should also know generally how to convert between those units. Okay, so this first problem, this is just a warm-up problem to make sure we know what we're doing when it comes to the ideal gas law equation. It says there's 3 moles of argon are stored in a 2-liter container that's kept at 10 degrees Celsius. What is the pressure of this gas? So what I always like to do, no matter if the problem looks easy or hard, no matter what, I always write out the variables that I know and the ones that I'm looking for. So here we know we have 3 moles of argon. And remember, guys, to take your own notes today because we can't share like these specific notes with you, okay? So try to do your best to take your notes today. The volume is 2 liters. The temperature is 10 degrees Celsius, and we're being asked for the pressure. So right away, it looks like I'm going to have to use the ideal gas law equation. Okay, and we're being asked to solve for pressure, so I'm just going to rearrange and solve for pressure by dividing both sides by volume. So I'm going to get pressure is nRT over V. Okay, now before you plug in, always just quickly double check to make sure your units all look good. So moles is fine, volume in liters, great. The temperature should be in degrees Kelvin. So we want to add 273, and that's going to get us 283 Kelvin. Okay, and then we're solving for pressure. So now we're just going to go ahead and plug those in. The R value here is something that's important. So here, if we look at the answer options all have the pressures in kilopascals. And depending on the unit of pressure, we said that's going to tell us what R to choose. So here, because the unit is kilopascals, the R value we'd want to choose is 8.314 for R. Okay, so we're just plugging in our values and we're going to be able to solve for a pressure. And I got 3,530, and the units are in kilopascals since we chose that R value. So this question was pretty simple. It's just a matter of rearranging the ideal gas law and plugging in values. So here we got our answer, and that answer matched D. Okay, so let's keep going. Let's see what other types of problems we might expect to see on the midterm. So the other thing we have to learn is how can we kind of rearrange that ideal gas law equation to solve for other things. So 2 common other variables that you might be asked to solve for are density and molar mass. So we're going to talk about how you can rearrange this equation to solve for both of those. Okay, and it all has to do with remembering that N, another equation for N, is that it's equal to little m over big M, where the little m is your mass in grams, and your big M is your molar mass in grams per mole. Okay, so here, what they did here was we want to solve for m over v in this case. So that's another equation where your density is equal to m over v, your mass over your volume. Okay, so in this case, I'm showing you how to rearrange the ideal gas law equation to solve for density. So first, they wanted to put the moles and the volume on one side. So we divided both sides by RT. So that crosses out RT. And then we divided both sides by volume to get moles and volume on the same side. So you end up with P over RT is equal to N over V. But then since they wanted to solve for density here, which is equal to mass over volume, instead of putting N, we plugged in little m over big M, which is equal to moles. Okay, and then finally, since I just wanted mass over volume on the left side, I want to get rid of that big M on the bottom. So I'm going to multiply by big M and multiply by big M here. So now I've just shown you guys how you can go from the ideal gas law to the density equation. Okay, so here's my tip is to make sure you feel comfortable with rearranging the ideal gas law equation like I just did to solve for, I just showed you guys density, and we can also look at how to solve for molar mass. So if I was instead interested in solving for a molar mass of a gas, well, that means we're just solving for this m. So what you would do is you would have little m, you would multiply both sides by RT. And since we only want big M on one side, now you'd want to divide both sides by pressure. And so now we have just solved for the molar mass of a gas. Okay, so you want to make sure you can do both of those and you'll be good for your exam. Okay, and then the little exam tip I have for you guys is something that I've noticed on past midterms, so I'll just mention that now so you guys can pay attention to that and remember that. But again, I'll remind you guys of these tips in the midterm exam prep session as well. But pretty much if they asked you to ever identify the unknown gas, and like they give you other variables like pressure, volume, etc., and they ask you, which of the following in options A through E, which of the following is the correct gas in our container? The way you would do that is you'd have to calculate for molar mass like we just did. So you'd solve for the molar mass, and then you would solve for molar mass of each of the gases in the options, and whichever one matches, that's the gas in the container. Okay, so now the next thing we're going to look at are gas laws. So gas laws are all going to be rearranging the ideal gas law when certain variables are kept constant. So here I've given you guys the name. You don't have to memorize that or know that at all. That's just, you might see these equations being referred to like as Boyle's law, Charles' law, but you do not have to know that. But what is important to be familiar with are the equations that we're going to get. Okay, so what I'm going to show you is kind of a trick you can use to easily get any of the gas law equations. And I've commonly seen at least one question on past midterms related to gas law equations. Okay, so certain questions might tell you that, okay, in this problem, there's a constant temperature and moles, or the moles of the gas is not changing, and the temperature they just said is this, and it doesn't change. So if you take the ideal gas law equation and you move all the constants to one side, so in this case, the constants are already on one side. N is a constant, we're told, T is a constant, and R is always a constant. So I'm just going to write it like this, PV is equal to constant, so we can see that a little better. And if we just take that, now that we have the constant all on one side, if I just repeat what we see on the left side of the equal sign, that's actually your equation. So it's a really simple way to get your gas law equation. So whenever T and N are constant, the equation we can use is P1V1 is equal to P2V2. So yeah, I showed my work on the right box, and that's the equation. And then if we're asked, are the variables inversely or directly proportional? How would we know that? So what I do for this is, if you look again at how we put the constant on one side, to see if two variables, pressure and volume in this case, are directly or inversely proportional, we want to look at them when they're on opposite sides of the equal sign. So I'd have to make them on opposite sides of the equal sign, so it would be constant over volume. And now that they're on opposite sides of the equal sign, we can see if they're both in the numerator or both in the denominator, that means they are directly proportional. So if one increases, the other one increases. But if we see like here, where one variable is in the numerator and the other is in the denominator, they're inversely proportional. So in this case, as pressure increases, volume would decrease and vice versa. So that I don't think you guys are commonly tested on whether variables are inversely or directly proportional. I haven't really seen any questions like that, but the equations are more important to kind of understand how you can get those. So we'll just quickly go through and just focus mostly on equations. So for the next one, when there's a constant pressure and moles, we can take PV is equal to nRT again. And we want to make sure that all the constants are on one side. So I want pressure moved to the right side, but I want temperature moved to the left side. So I'm going to have V over T, since I divided both sides by temperature. And I'm going to divide both sides by pressure. So it looks like this. Okay, so now that it's V over T, the whole right side is a constant. And we said once we have figured out, okay, the constant's all on the right side, we now have our equation. So we just V1 over T1 is equal to V2 over T2. That's our equation. Perfect. Okay, and then to figure out if two variables are directly or inversely proportional, you want to compare them when they're on opposite sides of the equal sign. So in this case, it would be V is equal to constant times temperature. And we see that they're both in the numerator. So that means they're actually going to be directly proportional. So if I increase volume, then that means there's going to be an increase in temperature as long as, again, we're in these conditions where there's a constant pressure and constant moles. Okay, so we'll keep working our way through this table. What about when instead we're told there's a constant volume and moles? What equation should I use then? So again, we're following the same exact procedure. So if there's a constant volume and moles, then we're going to have P over T, since those are variables that are not constants. And then the moles is the constant, R is a constant, and I'm going to divide both sides by V, which is also a constant. So now I have P over T is equal to a constant. And so now you can see that the equation we get is P1 over T1 is equal to P2 over T2. So if we want to know if they're directly or inversely proportional, we're just going to rewrite this, make sure the variables are on opposite sides of the equal sign. Okay, and then here again, we see that they're both in the numerator. So that means they're directly proportional. If I increase one of them, the other one will also increase. Or if I decrease one of them, the other one will also decrease. Okay, so there's two more equations. The next one is if there's constant pressure and constant temperature in the conditions. Okay, so pressure is a constant, so we'll divide both sides by pressure. And temperature is a constant, but I need to move moles to the other side since it's not a constant. So I'll divide both sides by moles and I'll get V over N is equal to a constant. So then my equation is V1 over N1 is equal to V2 over N2. And how are the variables related? Volume and moles. So I'm going to have you guys vote on this one. Let's see. So vote A if you think V is directly proportional to N, and vote B if you think V is directly proportional to 1 over N. Okay, nice. So here, to figure this out, we want to make sure the variables are on opposite sides of the equal sign. So right now they're both on the same side. We can't evaluate it right now. So we have to make sure that the moles is on the opposite side. So I'll multiply both sides by moles and get V is equal to constant times N. And now that they're on opposite sides of the equal sign, we see that they're both in the numerator, so they have to be directly proportional. So that's why A was right. Okay, so if we increase the volume, then I'm increasing moles. And then finally, if we just have constant moles, so if you look at PV is equal to nRT, so then N and R are the constants, so we can divide both sides by temperature, so you get PV over T is a constant. And so then your equation is P1 V1 over T1 is equal to P2 V2 over T2. Okay, and we can just, this one is not applicable. So how do I know whether I should use one of these gas law equations or if I should use the ideal gas law? And a big hint is if you're told there's some initial scenario and some final scenario. And there's lots of different ways that could be worded. They could say, okay, the initial pressure is this, and then, you know, the temperature is changed. So what is the final temperature? Like there's lots of different ways of wording that. But as soon as you can recognize that there's an initial scenario and a final scenario, then you know you're going to be using one of these gas laws and not the ideal gas law equation, since this one has 1s and 2s, or you can write I's or F's for initial and final volumes or temperatures or moles or whatever it is. Okay, so let's see if we can do this and if we can choose the right equation to use. So this one says a tank of gas has a pressure of 5 atm at 25 degrees Celsius. At what temperature will it reach a pressure of 8 atm? So I would first write out the variables. So it tells us the pressure is 5 atm. the temperature is 25 degrees Celsius. And then they say at what temperature. So now you can already recognize that, okay, we have a second scenario here. So they're now asking, what is the second temperature? And the pressure is going to be 8 atm in the second scenario. So that's the second pressure. So that means these are your initial pressures and temperatures. So here, because we only have pressures and temperatures, they haven't mentioned anything else, you can assume that those are constants. So if we have PV is equal to nRT, we want an equation that just has pressures and temperatures in it. So everything else is a constant. So that means I'm going to move V to the other side by dividing both sides by volume. Okay, and I want temperature on the left side because it is changing. It's not a constant. So I'm going to divide both sides by temperature. So I'm going to get P over T is equal to a constant. And so now we know how to get the equation. The equation is just P1 over T1 is equal to P2 over T2. Okay. Oops, so the second pressure, we know it's 8 atm. Okay, so now you could rearrange this to solve for T2. So we can go ahead and do that. So if you multiply both sides by T2, on the right side, it's going to get completely crossed out. And on the left side, you're going to have P1 times T2 over T1, and that's equal to P2. Okay, since I want the second temperature on its own, I now want to multiply both sides by the T1. So that's going to cross out the temperature here. And then I want to divide both sides by the first pressure or the initial pressure so that I've isolated for this final temperature. Okay, so now I have my T2 is equal to the final pressure, which we have written as 8 atm, the initial temperature. Now, again, remember that anytime we're using these gas equations, we want to make sure we're plugging in a temperature that has Kelvin. If you were to plug in degrees Celsius here, you're actually going to get the wrong answer. So make sure you add 273 to convert that into Kelvin. So here it would be 298. So we're going to multiply by 298. And then we're going to divide by the initial pressure, which we're told is 5 atm. Okay, and then when you plug that into your calculator, you're going to get 477 Kelvin. But then when you look at the options, they're all in degrees Celsius. So we're going to have to convert to degrees Celsius. So remember that if you have a temperature in degrees Celsius, you add 273 to get Kelvin. So if you have a temperature in Kelvin and you want degrees Celsius, we're just going to move this over. So we change its side and we change its sign. So the temperature in degrees Celsius is Kelvin minus 273. So if I take 477 and subtract 273, you get around 204 degrees Celsius. And so here the closest option was B, 200 degrees Celsius. Yeah, so someone's asking, should we always use the temperature in Kelvin for any gas calculation? Yes, definitely. You want to use Kelvin. Okay, and I know this question might seem a little bit simple, but on the first page of the past midterms every year I've seen, there's always one question on gas laws. So it could be any one of these gas law equations that we just went over. Okay, so I put an exam tip to remind you guys that you can definitely expect to see a question on your midterm that requires you to use one of the gas law equations. Okay, the next concept that we're going to take a look at is partial pressures. So first, we'll just learn about what is partial pressure. What does that mean? So if we look at air. Air is actually a combination of a lot of different gases. It's a mixture. There's not just one gas that makes up air. So these are some of the gases that make up air. And what this is showing is that each one of them has an individual pressure, which we actually call a partial pressure. So oxygens is written, nitrogens, argons, water vapor, and carbon dioxide gas. Those are all of their partial pressures. And if that's our mixture, if I add up the individual partial pressures of all of the gases in my mixture, that's actually going to get me my total pressure. Okay, so that's summarized by this equation here. So this one's nice and simple. Your total pressure in a container, you get that by adding the partial pressures of each of your gases in that mixture. Okay, now what is the actual definition of partial pressure? It's the pressure that the gas would make up even if it was, if you took that same gas, so if we took oxygen and put it in the same size container, that's the pressure that we would measure. So that's what it's kind of showing you. If you took oxygen and measured its pressure in a container, you would get the partial pressure of 20.9. Okay, so the partial pressure is the pressure that's exerted by one of those gases if it occupied the same volume on its own. So there's one more really important equation when it comes to partial pressures. And that is this one over here in a box, where this PA is representing the partial pressure of gas A, and the P total is your total pressure of your whole mixture. And I can actually solve for the partial pressure of my gas if I know the moles of my gas A and the total moles. So if I know the moles of my gas A, I can divide by the total moles. That's going to give me some fraction. So it's going to be a molar fraction. I know how much, what proportion of the mixture that my gas A that I'm interested in makes up. So then I multiply that by the total pressure, and I know now the partial pressure that my gas contributes. So another way to write that mole fraction, this NA, the moles of my gas A over the total gas, is X. So X just represents mole fraction. So just to help us think about this, let's say your gas makes up, let's say argon gas makes up 1 mole, and in total there are 2 moles in your whole mixture. So your mole fraction in that case is 1 mole over 2 moles. And let's say the total pressure is 10 kilopascals. So then the partial pressure for argon in our example is you'll take the X, you'll multiply that by 10. And so in this case, it's 1/2 times 10 kilopascals. And so argon in our container, in this random example, its partial pressure is 5 kilopascals. Okay. Now, this next equation isn't as important. It's just showing you again that mole fraction. So you take the moles of whatever gas, so gas 1 over the total moles. And it's just reminding you that you can use the ideal gas law equation to also calculate moles. So if you're interested in the total moles, you might also be able to calculate that. If they don't actually tell you mole values, you could use the ideal gas law equation, which we know is PV is equal to nRT. And if you solve for n, so you're going to divide both sides by RT, you're going to get PV over RT. But if you're trying to solve for the moles of one gas, we know that we just use the partial pressure of that one gas. On the other hand, if you're trying to solve for the total moles, so if you want to solve for total moles, then the pressure that you're going to want to plug into the ideal gas law equation is the total pressure. Okay, so that's just what this equation is showing you, but the 2 in the boxes are a lot more important for your midterm. Okay, this next one is very similar to the one I just showed you, so just make sure that if you're calculating a total pressure, then you're considering the total moles, and total moles is just looking at all of the different moles of gases in your mixture. So if there's 3 gases in your mixture, then you have to add up all of their moles to get total moles. And this last equation, there's usually a question on the midterm related to this average molecular weight equation. And we'll look at a question that involves this too, so we'll do some practice. But pretty much if you have if you have one gas, we know how to get the molar mass. You just look at the periodic table and the mass is written right there. That's the molar mass. But if you actually have a mixture of gases, you could be asked to solve for the average molecular weight of that mixture of gases. So that in order to do that, you're going to take the mole fraction of each of those gases, and you'll take the mole fraction for one of the gases and multiply by its molecular weight or molar mass. And then you'll take this sum and you'll repeat that for each of the gases in your container to then get an average molecular weight for that mixture of gases. Okay, so there's a couple of questions. So is a gas's partial pressure affected by its abundance in the mixture? That's a good question. So if you look back at the equation for partial pressure, we can see that the partial pressure does depend on the amount of gas in that container. So if the gas makes up a higher proportion, it makes up more moles. So let's say if our argon actually made up 75% of the moles, so the molar fraction was actually 3/4, then the partial pressure of it would be higher. So it would be 7.5 kilopascals. So if the molar fraction for a gas is higher, its partial pressure is also higher. So the next question is, does only moles of gas affect partial pressure? Yes, so you only ever have to think about how moles affects partial pressure. Okay, this next little equation that I've written here is actually exactly the same as the one we already took a look at, where we looked at the ideal gas law and how to solve for molar mass. So molar mass is mRT over PV. And in the equation I've written below, I just substituted m over v for density, which is like that really weird S symbol. So you have RT over P is another way of writing the molar mass of a gas. So if you're just interested in the molar mass of a single gas, you can use this, the density of that gas, RT, and the pressure of that one gas. And then what I'm saying down here is that if we're instead talking about a mixture, here you would be plugging in the density of that mixture, the temperature for that whole container, the total pressure, and then you have your average molecular weight that you could also solve for this way. Because this is going to help you calculate the molar mass of that container, the average molecular weight. Okay, so let's try some examples. The first one says a container holds a mixture of nitrogen, argon, and methane gases. The partial pressures are 500 torr for nitrogen, 300 torr for argon, and 200 torr for methane. What is the mole fraction for methane? Okay, so let's write out what we have and then we can see how we can solve for this. So this one is a bit of a simpler problem and it's going to help us prepare for more difficult problems. So we're told we have nitrogen, argon, and we have methane, which is CH4, but that's not important. The partial pressures are 500 torr, so we know the partial pressure, which you'll usually see like a little I to represent partial pressure, is 500 torr. The partial pressure for argon is 300 torr. And the partial pressure for methane is 200 torr. What is the mole fraction for methane? So I see that they're mentioning mole fraction, and I also see that we're talking about partial pressures. So the equation that should come to mind is the one where we mentioned that we can solve for any partial pressure of a gas if we have its mole fraction, and then we can multiply that by the total pressure. Because remember, if we have some proportion, you multiply that by the total pressure, you're going to get the partial pressure of that gas. So here we're interested in the mole fraction for methane, or X. So we can rearrange this equation to solve for X. So I'm going to divide both sides by the total pressure, PT, to solve for X. So big X is equal to, we're going to take off the PT since it crossed off, and you're going to get the partial pressure, we're interested in specifically methane, over the total pressure. So here we're actually told partial pressure of methane, and it's 200 torr, so we can plug that in directly. So we have 200 torr over the total pressure. So that one, remember, to calculate total pressure, you need the partial pressures of each of the gases in the mixture. So here we have nitrogen, argon, and methane, and we're actually given all of their partial pressures. So we can calculate the total pressure by adding up those partial pressures. So 500 torr plus 300 torr plus 200. And so you get 1,000 as your total pressure. And so now we plugged in our partial pressure, we can plug in our total pressure. And you're going to be able to solve for X, or your molar fraction. Okay, so that's your answer for methane. This is the molar fraction for methane. So just a question here. How do you find the overall density of the mixture? So that's a good question. You would either be given that value, so this is the density of the mixture. I've seen that in questions. Or another type of question that I've seen is you have to calculate the average molecular weight using this first long equation. And if you're being asked to solve for the density of the mixture, you then rearrange the second equation, plug in the average molecular weight, and solve for the density of the mixture. Okay, and we're actually going to look at a problem kind of like that, which I think is next. So this one is another question. It's saying a flask contains a mixture of propane and butane, and it tells us their partial pressures. So 75 kilopascals and 28 kilopascals are the partial pressures. If the temperature is 38, what is the density of this mixture? Okay, so this is exactly what that student was asking. What's the density of this mixture? So how do we calculate this? So the first thing we can do is we can recognize, okay, we're being asked about gases. And for density, there's a way to solve for density using that ideal gas law equation. So if you take the ideal gas law, this would be good practice now to try and see if you can rearrange this to solve for density. So you have to remember that to solve for density, you need m over v. That's the equation to solve for density. So PV is equal to, remember also that N is equal to little m over big M. So I'm going to plug that in, little m, and it's going to be over big M. And then we want the volume to be on the right side, so I can divide both sides by volume. So you're going to get little m RT over big M over V. And now you want the other variables to be moved to the right side. So that means I'm going to have to multiply both sides by big M and divide both sides by RT. And that's going to give you mass over volume, or density. Okay, so right now we've just solved for density of the mixture. We can plug in a pressure of the mixture. So you don't want to plug in a partial pressure here. You'd want to plug in a total pressure here. And molar mass, you'd actually need to plug in the molar mass of the mixture here, since you're being asked to solve for the density of the mixture. So we're really interested in the mixture, not just one gas here. Okay, and the temperature we can plug in, we'll convert it into Kelvin and plug that in, and R, we can figure out what unit to use there. So it seems like, first of all, we need to solve for the total pressure of this mixture, since we're interested in a mixture. And it just tells us that our mixture is made up of two things, propane and butane, and we're given both of those partial pressures. So we can add those together and we know the total pressure then. So it's going to be 75 kilopascals plus 28 kilopascals. And so when you add that together, you get 103 kilopascals. Okay, so now I solved for my total pressure of my mixture. I've rearranged to solve for density, so that's good. R, what value of R do you think I should use? So think about that. So the R we can use is either 8.314 or the 0.082. So we said we want to use that 8.314 value whenever the pressure has units of kilopascals. So here you want to use R is equal to 8.314. Okay, so we also have R. And temperature, we're told that it's 38 degrees Celsius. And remember, again, to convert that into Kelvin, so you're going to add 273, and that's going to give you temperature of 311 Kelvin. So we also have the temperature. Now we're missing the molar mass of the mixture. So we talked about how we can solve for the molar mass of a mixture, and it's going to be using this equation that we took a look at, the average molecular weight for a mixture of gases. So I'll just rewrite that equation to see if we can use it right away. So we said that what we're going to do is, in this case, we have two different gases. We're told one of them is propane, one of them is butane. And so we're going to take the mole fraction for propane and multiply by the molar mass of propane. And then we're going to add that to and do the same thing for the other gas in this mixture, the mole fraction of butane, and multiply that by the molar mass of butane. So before I plug in values, let's see if we actually have everything we need to solve for the molar mass of this mixture. The molar mass of propane, it's given in the question, so that's good. We have that. The molar mass of butane is also given. It would be given. So we have that as well. But now X, the mole fraction of propane. How do I solve for that? One second, there's a question. So someone is asking, why can't we just add up molar masses? That's a really good question. So yeah, we do know the molar masses of both of these, but it would actually be a mistake if you just did 44 plus 58. The reason for that is because let's just think of this in terms of dots so we can understand. Let's say that I had one dot of propane, but my mixture actually has 99 dots of butane. Let's just keep going and going and going and going and going. And we see that butane has a higher molar mass. So therefore, my mixture is going to have a molar mass that's closer to butane's number. And so that's why this isn't just adding up molar masses, this calculation. It's taking into consideration how much of that gas we have. So that's why the mole fraction is really important to remember. You multiply that by the molar mass for that gas. So that's why it's called a weighted average. We're taking into consideration how much of that gas is there. That's a really good question. Okay, so exactly. So someone already figured this out, how we can solve for the mole fraction of gas, of the gas. So if you forgot, I remember seeing mole fraction in one of those equations where we looked at the partial pressure of a gas is equal to the mole fraction of a gas times the total pressure. Now here for propane, I know another equation for the mole fraction is if I had the moles of that gas over the total moles. So here I don't have any information on moles, so I can't use this second equation. That's not going to be useful to me at all. But the first equation is going to be useful because I can solve for the mole fraction by doing Pi over Pt for a gas. And I have each of their partial pressures, and I also calculated the total pressure. Okay, so that's what we're going to do for each of these gases. So the weighted molar mass is equal to the mole fraction of propane. So we said that is equal to the partial pressure of propane, which is given to us. So the partial pressure of propane, it said it's 75 kilopascals. We said over the total pressure. And we solve for that here, 103 kilopascals. So that's the mole fraction. And now I'm going to multiply by the molar mass of propane, which were given in the question, 44.10 grams per mole, plus. And now we're going to do the same thing for butane. So we have the mole fraction of butane. You're going to take the partial pressure of butane, which is 28 kilopascals, over the total pressure of butane, sorry, the total pressure of the whole container, which we found to be 103 kilopascals. And then multiply that by the molar mass of butane, so 58.12 grams per mole. And so when I calculate this, you're going to get 1.908 grams per mole. Okay. And then finally, we just have to solve for the density of the mixture. So we're going back to this equation here. So we're interested in the density, which is m over v, and that's equal to the total pressure times the molar mass, the average weighted molar mass of that mixture over R times T. So the total pressure we already found, and that's 103 kilopascals. The average molar mass or weighted molar mass of this mixture is 1.908 grams per mole. R, remember we want to use 8.314 here because the pressure has units of kilopascals. And temperature, you want to make sure you're plugging in Kelvin, so that's 311 Kelvin, we said. And now we've just solved for the density of the mixture. So the density of the mixture is 1.91 grams per liter. Okay. Yeah, I'm going to double check this calculation during the break because I'm not sure if this number, but it's going to take me a while to plug that into my calculator. So I'll do that during the break and come back to you guys. But I want to do one more problem with you guys before we go for a break. Okay, so this question, something like this is actually commonly seen on the midterm. So I wanted to do one question now and also one question in the midterm prep session so we can really understand this question since it's pretty much seen every year on the midterm. So it says, consider the apparatus shown in the drawing below. At first, the stopcock, which is this thing right here, it's keeping the gases separated at first between both flasks, is kept closed. When the stopcock is open and the gases are then allowed to mix, it wants to know what is the partial pressure of nitrogen after mixing. Okay, so originally you have two containers or two flasks, and we're told in this case we have the volume, we have the pressure, we have the temperature, and the same thing for oxygen. And so that's in the first scenario. But then when the stopcock is opened, what's my new volume? So this part is, we can solve for this right now. The new volume is just by adding those two volumes together. So if you take your V2, we can just say, or your total volume, right? The total volume is you just add up those initial volumes. Since now we're allowing those containers to be connected. So it's now 6.5 liters. Okay, so that's one thing, and that's always going to be the case for any of these flask problems. Okay, so now we have to let's think of just nitrogen for a second. So at first we had it in one container, and now we have it kind of, when the stopcock opens, it goes in a giant container. And that's all you have to think about. We can actually ignore oxygen completely here because of the definition of partial pressure. So remember, partial pressure is saying that even if we have a mixture of gases, the partial pressure of nitrogen is looking at what pressure nitrogen would have if it was alone in that container. So we can ignore oxygen here. So what this question is pretty much saying is you have this initial scenario, and in the final scenario, when the stopcock is open, what is the pressure? Okay, so this question is another way you can think of it is that other variables are kept constant. And P and V are changing. So they're not constant. So then if we remember the ideal gas law equation, we said that all the other variables are constant, so we can just write PV is equal to constant. And so now I know that P1 times V1 is equal to P2 times V2. So that's the equation that I'm going to use. But this is, I'm just again thinking about nitrogen. So now I'm interested in nitrogen's second pressure, or the pressure in the second scenario after the stopcock is open. So I want to solve for P2 by dividing both sides by the volume, by the second volume. So you have P1 V1 over V2, and that's going to equal P2. So now you just have to plug the values in. So the first pressure that nitrogen had was 2 atm. And the volume at first was just 2.5 liters when it was alone in that container. Okay. And the final volume is like the volume in the second scenario, or the final volume, that's the total volume. Once the stopcock opened, nitrogen is now allowed to take up that entire volume. And so we're going to use that 6.5 liters here. Okay, and so what you should get when you plug that in is that the partial pressure of nitrogen is 0.77 atm. So that's just the pressure of nitrogen after we mix the gases and we open the stopcock. Okay, so I know at first these types of questions seem pretty difficult, but the nice thing about them is that it's actually just like P1 V1 is equal to P2 V2, because all the other variables are constant except for pressure and volume. So if we just think of one gas at a time, we can use this equation. And that's how I knew that, okay, even if I open the stopcock, there's a larger volume, but if I solve for pressure of nitrogen, that is the partial pressure of nitrogen, which is what this question is asking us for. Okay, so that was the second pressure. Okay. So someone's asking about the temperature, they would tell you that the temperature is changing. So as long as they don't mention temperature, or in this case, like it says that it's at the same temperature, you can just assume that it's constant. Okay. So the last thing that we'll talk about before we go for a break is we're going to touch on gas reaction and stoichiometry. Okay, so we're probably familiar with stoichiometry, where you can look at a balanced chemical reaction, and let's say there's 1 mole of this substance. Then we know that if that goes to products, let's say there's 1 mole of this, and in the balanced chemical reaction there's 2 moles of this. If I have 1 mole here, then I know I'm going to have to multiply by 2 to get 2 moles of this product, let's say. And so we're very familiar with using moles. But for gases, we can sometimes use volumes and pressure instead. And we'll talk about when that is, and it has to do with conditions. So when we have a constant temperature and pressure, if we go back to this table, when we have a constant pressure and temperature, we realize that the volume is directly proportional to moles, okay, because everything else is constant. And so in that case, if they tell you that pressure and temperature are constant, and they only give you liter amounts, and they're asking you how many liters of this product can we get, then you can just use liters as you would moles. So you don't have to actually have to convert everything into moles. You can use liters as if they are moles. Okay, so that's what this is saying. So in those conditions, you can treat volume as moles. And similarly, if instead you have a constant temperature and constant volume, if we go back and see the equation that we created when we had constant temperature and constant volume. Oh, okay, we don't have one like that. So let's go back and see what would how the variables would be related. So in constant temperature and volume, we have PV is equal to nRT. So V, T, and R are constants. So I want to move V to the other side. And N has to be on the left side since it's not a constant here. So you're going to get P over N, since we had divide both sides by N, is equal to RT over V, which is a constant. Okay, so here, now we know that how are pressure and moles related? Well, we said that they have to be on opposite sides of the equal sign. So P is equal to constant times N. And so I know that because they're now both in the numerator, they're directly proportional. So P is directly proportional to N. So in these conditions, under constant temperature and volume, we can treat pressure as moles if we're just told about pressures. Okay, we'll look at examples of this. So the first example is saying that bromine and fluorine can react to form BRF5 according to the following unbalanced reaction. And we want to know how many liters of that compound can be produced at this temperature and this pressure if this many moles of fluorine are reacted with an excess amount of bromine. Okay, so right away for any stoichiometry problem, the first thing that we want to do is we want to make sure we're looking at a balanced reaction. So here it outright said this is an unbalanced reaction, but on a test it's not going to say that. So make sure that you check to make sure that it's balanced. Okay, so on the left we have 2 bromines, and on the right we can put 2 bromines, so we would need to put a 2 there. And now on the right, we have 10 fluorines. On the left, we only have 2, so I'll need to put a 5 here. Okay, so now our reaction is balanced. So the next thing we're told is that we have 18 moles of fluorine and an excess amount of bromine. So that just means that the one that's limiting in a limiting amount, that's going to control the amount of product we get. The excess one doesn't determine the amount of product we get. So now that we have the limiting reagent, it's asking us how many liters of the product can we get. So right now, since we have moles, what we can do is first determine the moles of our product that would be produced. And then once we have moles, let's see if we can use the ideal gas law equation to solve for the liters of that product that's produced. Okay, so let's just do step 1 first, where we were told we have 18 moles of fluorine. So we have 18 moles. And now we need to take into consideration those stoichiometric coefficients in that balanced reaction. So you're going to multiply 2 moles of BRF2, and you're going to put the moles of fluorine or its coefficient. So here we put the coefficient of BRF5, and then the coefficient of F2 in the bottom. So 5 moles of F2. So this is saying for every 2 moles of BRF5 that I get, I need 5 moles of F2. And I put the moles of F2 on the bottom so they can cancel out with the moles that we have of fluorine. And so now when you calculate that, you're going to get the moles of BRF5, so the moles of the product. So you should get 7.2 moles of BRF5. But we're not interested in the moles of BRF5 for this answer. We want its volume, or the liters. And so now we can use the ideal gas law equation and see if we can use this, where we should try to rearrange the solve for volume and see if we can solve for it. So V is equal to nRT over pressure. So we have 7.2 moles, plug that in. R, well, R again depends on the pressure units. So here we're going to plug in a pressure that is in units of ATM. So the R value we want to use is the one that has units also ATM. So it's 0.08206 ATM liters per mole K. Okay, the temperature, we want that also in degrees Kelvin. So you're going to add 273 to get the temperature in Kelvin. So that gets you 316 Kelvin. And then you're going to divide by the pressure, which is 1 ATM. And so the answer for the volume, it's 186.7 liters. So it'd be A. One second. So for this problem, you had to first figure out how many moles of the product we could get just based on looking at the stoichiometric coefficients in this reaction. And so that's like what we were very used to doing. And then the only difference here was that it actually wanted you to solve for volume. So once you had moles of our gas, we wanted volume of our gas. And so you had to plug that into the ideal gas law equation. Okay, we'll see a different type of problem. So this one says at constant temperature and pressure, okay, so telling us that variables are constant, 2 liters of hydrogen is mixed with 3 liters of chlorine gas to produce HCl gas. How many liters of HCl gas will form? So here it looks like a chemical reaction is happening. So what we want to do is we actually want to write out a chemical reaction if one is not given to you. And I have actually seen a question on a past midterm that actually made you write out the reaction. So here we have H2 plus Cl2, and we're told the product. So it would look like this. And then we just have to make sure that we also remember to balance that. So we would have to put a 2 there, and now it's completely balanced. Okay, so the next thing we're told is volume. So we're told we have 2 liters here as the volume and 3 liters here is the volume. And we're asked, what is the volume of HCl, hydrochloric gas in this case. So now, do I have to convert to moles of each and then figure out moles of my product and then figure out volume? Or is there a simpler way? So here we're told that there's constant temperature and pressure. So if we look up, whenever you have constant temperature and pressure, you can treat volume as moles. And again, if you forgot that, or if you want a way to remember that, you can just use the PV is equal to nRT method that we saw. So temperature and pressure and R are constants. You want to move that to the right side. So V, divide both sides by P, and then divide both sides by N since it's not a constant. And so now we can see that, oh, okay, in these conditions, volume is directly proportional to moles. So instead of using moles, we can actually just use volume, and it's a lot simpler. So now we know we can use volumes as we normally would use moles. So we are using volumes in the place of moles. So the first thing we have to do, because we now have 2 reactants, we're not told which of them is limiting or which one is in excess. We first have to figure that out. So the way to do that is you take the amount of liters in this case and you divide by the coefficient in the reaction for both reactants to see which one you have a smaller amount of. So for hydrogen, you have its volume divided by its coefficient. And for chlorine, you have its volume divided by its coefficient. And so here you can see that we have less hydrogen, and so it's going to be the limiting reagent. So hydrogen is the limiting reagent. And so we're going to use the volume of hydrogen to figure out the volume of HCl that's going to be produced. So if we have 2 liters of hydrogen, then we're going to get, because of the coefficients, you're going to multiply by 2. That's going to give you 2 liters of HCl for every 1 liter of hydrogen because of its coefficient. Okay, so we had 2 liters of hydrogen, and then the liters hydrogen unit cancels out. And we're going to be solving for the liters of HCl. So you're going to get 4 liters of HCl, and that's going to be your answer here. That's how much, that's the volume of product that we would get. Now, another question that I've seen on past midterms is if it instead just said, after this reaction takes place, what is the final volume? So I want you guys to do this one, and we'll vote on the answers. Okay, so let's see how we would calculate this. So here we had a limiting reagent, which was hydrogen. And so that means that from this reaction, we're actually going to completely get rid of all of the hydrogen. It's going to completely react. And so at the end of the reaction, the amount of hydrogen you have is 0 liters. It's completely reacted. Now for chlorine, you reacted 2 liters of hydrogen. And so for the 2 liters of hydrogen, we can see that they have a 1-to-1 ratio. So that means 2 liters of chlorine would have reacted, and you have 1 liter of chlorine left over. So there is 1 liter left over. Okay, and then we already talked about how for hydrochloric acid, 4 liters was produced. So your total volume, you're just going to add that together. 0 plus 1 plus 4, and you're going to get 5 liters as the total volume. So that's why the answer here was E. Okay, so on a more complicated problem, you'd have to solve for the volume of chlorine that we used up. So here, because I knew that we are using up 2 liters of hydrogen and I wanted to know how many liters of chlorine would I have to use up, you'd plug in their coefficient. So it's just 1 liters of chlorine for every 1 liters of hydrogen. This is kind of like the way of writing this out in a chemical reaction. And then that would help you, well, we'd cross out the units for liters of hydrogen. We'd solve for the liters of chlorine that we would be using in this reaction. And you would get 2 liters of chlorine that's used. And so you know that because we had 3, we know that we had 1 liters left over. Okay, so that's why the total volume was 5 liters. So the limiting reagent, hydrogen, is always going to be completely used up. Okay, so I think that's a good place to take a break. So we'll come back at 5:20 and we'll continue the rest of the booklet then. Okay, so we're going to get started again. I just wanted to quickly start with this problem here that we looked at on page 7. Yeah, I noticed the answer I originally had there for the average weighted molecular mass was wrong. I just put in the wrong number in the solution. So make sure that you guys change this, 47.91 it should say, and then we just plug that into the density, but the answer for density should be 1.91. Okay, and for the student who asked again, like, why do we calculate the average molar mass? Well, now it makes a lot more sense because if you look at how we had one molar mass that was 44 and the other one that's 58, but the propane that made up more of the fraction of this mixture, it makes sense that the weighted molar mass is actually closer to the molar mass of propane. So that's why it's 47, and that makes sense. So that's how you can check your answer. Okay, so now we're going to be looking at kinetic molecular theory, and we'll just go into a couple of different scenarios related to that. And then we'll finish up with gases, and we're just going to start thermochemistry today. Okay, so the kinetic molecular theory, we should know what it says, and I think I've seen one question on a past midterm where it says, which of the following is not something that the kinetic molecular theory says. So it's going to be helpful to familiarize yourselves with these points, but it also helps us understand, again, ideal gases. So ideal gases are gases in an ideal situation. This is not how gases act in real life, but it's easier to think of them like this for our calculations. So the first thing that the kinetic molecular theory says is that gases are in constant random motion. So they're always going to be moving. They don't ever stop. So once it hits this wall, it can then bounce, and it's just going to be in constant random motion. Okay, and you can see that because it's in a container, there's also a lot of collisions. And so we know they're in constant random motion. And so the kinetic molecular theory also says something about those collisions. Now, the reason why is because if a gas lost energy every time it hit the container walls, by the end of it, it would have like no energy. And so that would not be ideal for our equations. And so that's why we assume that all of the collisions are completely elastic, meaning that the energy is conserved before and after collision. So the gas particle is not losing energy each time they collide with something. Okay, another assumption that we make for the kinetic molecular theory is that the volume of the gas is just zero. So we say that, okay, because the container is so big, let's just say that the volume of the gas is actually zero. The volume of the gas itself is zero. And so all of the volume in the container, we're just going to assume that just is the volume of the container, and we don't have to ever account for the volume of a particular gas. So for example, in the PV is equal to nRT equation, that volume is the volume of the container. We never are interested in like the volume of these tiny, tiny gas particles and how much they take up. So we just completely say that they have a volume of zero. We don't even deal with that. The next assumption is that there are no attractions or no intermolecular forces or attractions between gas particles. So it's just a lot easier to not have to deal with those intermolecular attractions. And so that's why we're just able to assume, okay, this gas is just randomly bouncing around in there, and there are no attractions or repulsions between anything. Okay, and the last thing that the kinetic molecular theory says is the relationship between temperature and average kinetic energy. And we're going to be going over this more, but we should know that temperature is directly proportional to the average kinetic energy. Okay, so that means if we increase temperature, do you think the gas molecules would collide with the container more or less often? So if you increase temperature, that means you're also increasing your average kinetic energy, which is the energy of motion. So then it makes sense that the gas molecules would collide with the containers more often. And if you increase the temperature, you're also increasing their motion. And so it makes sense that they should be at greater speeds in general. Okay, these next scenarios are not super commonly tested on, and I do have one question at the end which is likely to show up on your exam, but I want to still go through these so you guys have a good understanding, because that is more important for the exam than the question. So here is below, we'll see the question and how this relates to the content, but just kind of sit back and just understand this part. Don't worry about memorizing. So the first scenario is when we have two gases and they're at the same temperature in different containers. And you could be asked about the average kinetic energy of those gases. Okay, and because we mentioned that the kinetic molecular theory says that temperature is directly proportional to the average kinetic energy, then if two gases are at the same temperature, they're going to have the same average kinetic energy. Okay, so that's just a relationship to know for your midterm, okay, just in case something like that comes up. The next thing that I also saw a question on was, it said that, okay, we have two different gases again, and they're at the same temperature, and again in two different containers, but this time we're interested in the speeds of those two gases, okay? So yes, they're at the same temperature, so they're going to have the same average kinetic energy. So again, they're at the same temperature, so they have the same average kinetic energy, even if they're different gases. But for this one, we have to consider the equation for kinetic energy, which is 1/2 mv squared. So we're not going to have to do any calculations, don't worry. But just for understanding, even if two different gases have the same average kinetic energy, so it's an average kinetic energy, they're actually going to be at different speeds because one of the gases is going to be heavier, so it's going to have a larger mass. And so that heavier one is going to have a smaller average speed or lower average speed so that it gets the same average kinetic energy. Okay, and that's what this graph is showing. This graph is showing, this plot is showing a bunch of different gases all at the same temperature, but notice how they're acting at different average speeds. So helium, the average speed of helium is around here, which is much higher than the average speeds of the other gases in those containers, because helium is a lighter gas. So if you are a lighter gas with a smaller mass, then your average speed is going to be higher. And you're still going to have the same average kinetic energy because you're at the same temperature. Okay, so that's how mass and speed can be related for different gases. The other thing to note that I saw a question on related to, it was talking about, are all of the helium particles, let's say, are all of them traveling at the same speed? So that's another mistake to avoid. You don't want to say that all of the helium particles are at the same speed. We can actually see a nice distribution here. So yes, on average, the helium particles are traveling faster than the other particles, but there's a distribution. So some of them are still pretty slow over there. Okay, so not all of the same gas particles move at the same speed. That's a key concept to understand. It's summarized below. We'll go over that. So just to summarize this, it says a heavier gas is on average going to move at slower average speeds than a lighter gas. And if it's lighter, it also has even more broad distribution that we see with helium. It can have, yes, it has a higher average speed. It can also have a lot of different speeds. Okay, so the exact past exam question related to helium and neon. So it said, the statement said, all of the helium particles move faster than neon particles. Is that true or false? So on average, helium is faster than neon because we know helium is lighter, but all of them don't move faster than neon. Some of them might be a little bit slower than some of the neon particles. Okay, so there's a distribution of speeds. Not all of the gas particles are going to travel at the exact same speed. Some are going to be slow, some are going to be a little fast. But on average, if you're looking at a lighter gas, that one is going to be at higher speeds. Okay? So this relates to this equation, the root mean squared speed equation. And this one is not commonly tested on, so we're not going to spend too much time here. But what's nice about it is that it helps us understand the relationships between speed and temperature and speed and molar mass. So we know that if we increase temperature, we can see that they're both in the numerator. So you're also going to increase the root mean squared speed, or that you can just think of it as the speed of a particle. And if you increase the molar mass, meaning you now have a heavier particle, then you're going to get a smaller root mean square speed. Okay? So just understand those relationships. So now I want us to try this equation and, this question, and we'll vote on it. This one is similar to one I saw in a past exam. Okay, start taking it up. I included this one because like the words just are confusing for students. So it just tells us there's two different gases. They're at the same temperature. Which of the following is the same? Okay, so right away we mentioned that because they're at the same temperature, we learned because of the kinetic molecular theory that temperature is directly proportional to the average kinetic energy. And we said that if you're at the same temperature, you have the same average kinetic energy, no matter what gas you're dealing with. Okay, so that's why the answer was D. And so these gases, helium and neon, they have different molar masses. So because of that, remember that root mean squared speed has to do with molar mass. So they're going to have different root mean squared speed since they have different molar masses. Okay, and so that's why A was incorrect. I know a lot of people chose A. Okay, so because they're at the same temperature, they have the same average kinetic energy. Okay, the last equation that we'll look at that relates to gases is Graham's law of effusion. And so this picture is just showing what effusion is. So if you see the term effusion, it's referring to, okay, we just start with this part on the left, and this part on the right is just empty. Okay, but what happens is that there's a hole in this container, and so the particles can slowly go through this hole. And after a certain period of time, we'll measure how many of each particle do we have on the right side. And so that tells us like how fast they were able to effuse. Okay, so just to see if we understand that concept before we go on, do you think, according to this image above, did the green or purple particles have a faster rate of effusion? We can vote on this one quickly. So here we're looking at them effusing into the container on the right. So the ones that moved into that container on the right faster, they have a faster rate of effusion, and we can see that there are a lot more green particles. So it makes sense that the green particles had a faster rate of effusion, since we see so many more of them on the right side after a certain amount of time. So if something has a higher or faster rate of effusion, it just means that those particles are escaping through that hole at a faster rate. So do you think lighter or heavier molecules are going to be able to effuse faster? So the ones that can move faster and effuse faster are the lighter ones. And so this brings us to this equation, which is important to know. So here we have Graham's law of effusion equation, where the rate of effusion for gas A over the rate of effusion for gas B. Another way of saying that exact same thing is the root mean squared of gas A over the root mean squared speed of gas B. And then just remember that when you're plugging values in, that we want to plug in the molar mass, they are opposite. So if you're dealing with the root mean squared speed of gas A on the top, then you want to put its molar mass on the bottom for this part. Okay, so then you take the square root of both of their molar mass, but just make sure that they are opposite. Okay, so what this is saying is that the root mean squared speed of, let's say, gas A, it's proportional to 1 over the square root of its molar mass, meaning that if I had a very, very heavy gas with a high molecular weight, it's going to have a very low root mean squared speed. It's not going to be moving very fast. So that's what this equation is pretty much showing us. Okay, so a couple questions. So why was green the answer here? So it was just saying, so pretty much at time 0, before you start the experiment, all of the particles are on the left side, and then there's a small hole. So after, let's say, 5 minutes, we see what we see on the right. And so I can see that a lot more green particles are there. So it must mean that green has a faster rate of effusion. They're able to go through that hole a lot quicker, and so they must be lighter. And no, it actually does not matter what you put as gas A or gas B. So let's say you have I don't know, two random gases, helium, neon. You can put helium on the top or the bottom, does not matter. Just make sure that if you put helium on the top, it's root mean squared on the root mean squared speed on the top. Its molar mass has to go on the bottom when you're putting in their molar masses, because they have this relationship between, they have an inversely proportional relationship between root mean squared speed and molar mass. So root mean squared speed is inversely proportional to the square root of the molar mass of that gas, which you wouldn't have to memorize or anything like that, but just know in general, the heavier something is, the slower it would be. The slower its effusion rate would be. Okay, so we can apply this to this problem here. It says a container has an equal number of black and white particles in one container. And after 2 minutes, 4 dark particles, so the time has gone by, 4 dark particles and 2 light particles had effused to the other container. How much heavier or lighter are the dark particles than the light particles? So, okay, so the first thing we see is that after the certain amount of time has passed, 4 dark particles were found on the right and 2 light particles were found on the right. Now, if you look at the options, some of them say that the dark particles are heavier and some say that dark particles are lighter. So vote A if you think the dark ones are heavier, or vote B if you think the dark ones are lighter, just based on the information right in the question. Okay, so because more dark particles effused, they effused at a faster rate, so they must be lighter. So they were lighter. And so option A says dark particles are heavier. That's definitely wrong, because we just know that dark particles are lighter since they effuse at a faster rate. And D also said that dark particles are heavier. So now we have to figure out how many more times are they lighter than light particles. So lighter in weight than light particles, it should say. So here we can consider the root mean squared speed equation. So let's say I'm interested in the root mean squared speed of the dark particles over the root mean squared speed of the light particles. And if I wanted to plug in the molar masses, then the molar mass I would have to plug in here for dark, and the molar mass here for whatever that light particle is. So now I'm going to have to try to plug in something so I can understand how their weights are related. And we said that for this equation, another way you can think of it is the rate of effusion of gas A over rate of effusion of gas B. So instead of writing root mean squared, we can write rate of effusion of the dark gas over the rate of effusion of the light gas. Okay, so here, the hardest part is figuring out the rates. So it says that 4 dark particles crossed for every 2 dark particles. And we can actually just plug that in for the rate. So there are 4 dark particles that went across for every 2 light particles. And so on the left side of the equation, you get 2 is equal to root the molar mass of the light particles over the molar mass of the dark particles. Okay, but I still have to relate them in some way. So let's do 2 squared and square the right side to get rid of the square root. So we now have 4 is equal to m light over the molar mass of the dark particles. And so now I can see that 4 times the molar mass of the dark particles is equal to the molar mass of the light particles. So given that information, now see if you can decide on what the answer should be. Exactly. So perfect. So based on this equation, we can see that I would have to take the molar mass of dark particles and multiply it by 4 to get the molar mass of light particles. So the dark particles are 4 times lighter than the light particles. Okay? So here we again just figured out that dark particles are lighter since we saw them effuse faster. And then using the root mean squared equation, we could actually see how the molar masses of both of those particles were related. We found the dark particles were 4 times lighter. Okay, so now we're going to spend the last bit of time to go over thermochemistry part 1. It's not too much information. We'll go over a couple key equations, and then next time we're going to cover thermochemistry part 2 and 3, which includes things like calorimetry and enthalpy. So a lot more equations and calculations for next week's session. So the first thing that we want to go over for thermochemistry is the difference between system and surroundings. Oops. So if we have a reaction flask, then the reaction itself inside there, that the reaction, that is considered the system. And everything else, the flask, the air, that's all considered the surroundings. Okay, and another way to think of this is that you have the system, which is your reaction, so your reactants and products. And then everything else surrounding that is your surroundings. And both of those together, when you take the system and surroundings, you get the universe. Okay. The next thing that we're just going to quickly review is the difference between different types of systems. And it's actually simpler than it sounds. So an open system is just like an open bottle where let's say you actually had a hot drink in here and you put your hands on that hot drink. Well, you know that heat can be transferred from, if it's a hot drink, the heat would go from the hot drink to your hands. So heat can go in and out of that container if it's an open system. And also energy and water vapor can also go in and out of the container. So in more science terms, we can say that energy can go in and out, and matter, so things can go in and out. So if I have an open cup, matter can go in and out. I can drop something in that cup. It's open to the environment. Okay. Now, if I have now a closed system, it's just like closing a lid. So matter or things can no longer go in and out, but heat energy is just an example of energy that can still be transferred in and out of the system. And then an isolated system is like a theoretical, ideal type of system. And this isolated system is when we talk about calorimeters, that's the type of system that they are. So it's like a perfect scenario where no energy can leave that isolated system. So there's no energy or matter that is in contact with that system. So everything is happening inside of that. Some other terms that you guys have to know, the first two are extensive versus intensive properties. So there's an easy way to remember this. Extensive just sounds like the extent of something or the amount of something. So this is a property that actually changes depending on how much you have. So for example, mass is an extensive property. If I have 7 bricks versus 1 brick, the mass is different, right? So that's how you know that mass is an extensive property. Whereas an intensive property, no matter how much you have of it, an intensive property does not change. So if I have 1 glass of water versus a pool full of water, the melting point of that water is something that does not change no matter how much water I have. So that's why we call it an intensive property. Okay, and on a past exam, students had to identify actually whether melting point was an extensive or intensive property. So it was a question that said, which of the following is false? Melting point is an intensive property was one of those. So you'd have to say, okay, then that's actually true. Melting point is intensive. It doesn't matter how much water you have. Its melting point isn't going to change. So melting point is an intensive property. The next two terms are exothermic versus endothermic. So exothermic sounds like heat is exiting the system. And we always think of it in terms of the system. So if something is exiting, if heat is exiting, like if we see the term exothermic, it's describing the system. So this means heat is exiting the system. So in other words, heat is being released from the system to the surroundings. Okay, and the opposite of exothermic is endothermic, which kind of sounds like indoors. So this one, heat is moving into the system. So heat is being absorbed into the system. Okay, and I think, yeah, these are the last definitions that you guys have to know. What is a state function versus a path function? So this is just a random example that you do not have to know, just to help you guys understand this. And it's looking at a person climbing a mountain. So if you wanted to take the scenic, or I guess if you wanted to hike, get some more exercise in, right? We can walk and get to the same point on the mountain. Versus if your friend wanted to take a helicopter, he starts at the same point you did, and he ends at the same point you do too, but he takes a completely different path to get there. Okay, so if we look at two different variables in this example, the change in altitude is the same. So they both have the same change in altitude. So we would say that the state function here is the change in altitude, because the definition of a state function is that it only depends on the current state. It does not depend on the path we take to get there. So no matter what path we took here, we took two different paths, but the change in altitude was the same. So that's why we say that's a state function. If a variable actually depends on which path you take, and it's different depending on which path you take, then that's a path function. So distance covered, it might take me 6 hours to climb this mountain. There's such a far distance, whereas up the mountain, up the helicopter, it's a much shorter distance. So the distance, depending on which way I took, was different. So that's why we say it's a path function. It actually does depend on the path you take to get there. Okay, now the nice thing for chemistry is that state functions are typically written all in capital letters. So these are all examples of state functions with all capital letters. Okay, so that's an easy way to remember that these are state functions. They don't depend on the path taken. So they are represented by capital letters, whereas on the other hand, your path functions are represented by lowercase letters like little q and little w. Those are path functions. And so on a past exam, the way that this came up was that you actually had to identify whether enthalpy was a state function or path function. So enthalpy is written as a big H, so that's already a hint that we know that it's a state function. And we'll later talk about how, when we learn about Hess's law, how you can add up the enthalpy in each step, and it doesn't matter the path that you take to get there, you can still find the enthalpy of the reaction by adding it up from each step. So because it does not depend on the path, enthalpy is a state function, okay? And the shortcut to get that same answer is remembering that all of these ones with capital letters are state functions. Okay, so the next thing we're going to look at is the first law of thermodynamics. And this one is pretty much saying, this law is saying that energy is not created or destroyed. And so the energy of the universe is equal to 0. Okay, so we'll talk more about that in just a second. This is the equation that we get from the first law, where, by the way, if you see delta E, it's the same thing. They both represent internal energy. Sometimes people write U, same thing, internal energy. But what we want to know is the equation is Q plus W. So we're going to talk a lot more about that equation in just a second, where Q is your heat and W is work. Okay, but let's just keep thinking a little bit about what does it mean that energy can't be created or destroyed in the universe. Okay, so since we can't create new energy and destroy it, I can only transform energy into different types. So for example, if I decide, don't memorize this at all, but just a random example, if I decide to eat an apple right now, that's going to give me some chemical energy. And then later, maybe I go to the gym. Well, we're in COVID, so I go downstairs to my basement. I start lifting some weights. So now that's mechanical energy. I'm doing something with my food energy or my chemical energy. So energy is transforming into different types. And then other energy, I'm losing energy as heat too when you feel hot and you start sweating. So energy is being transformed into different types, but energy is not, we're not completely getting rid of energy at all. So the change in energy of the universe is zero. And we said that the universe's energy and the universe in general is made up of the system and the surroundings. So this you don't have to memorize, but I'm just trying to show a relationship. So if I actually move the change in energy of the system over, we get an interesting relationship, and we just want to understand this, not memorize this. So what this is saying is that any change in energy that happens to the system, it's going to have the same magnitude of change to the surroundings, but just opposite sign. So if the system gains 5 joules of energy, then that means the surroundings will lose. That means the surroundings lost 5 joules of energy. So the surroundings had to lose 5 joules of energy. That's how the system gained 5 joules of energy. The 5 joules of energy didn't just come from thin air, came from the surroundings. Okay, on the other hand, another example is if the system loses 10 joules of energy, then that 10 joules of energy is gained by the surroundings. Surroundings gains 10 joules of energy. Okay, so they're going to have the same magnitude, opposite signs. And when we talk next time, this is going to come in handy when we talk about calorimetry. Okay, so there's just a couple pages left. Stay with me, you guys. So we talked about this equation. This is your first law equation. And something that's often confusing for students is the sign of each. So we mentioned we have Q and we have W. Sorry, so we have heat and work. Now, each of those variables, Q and W, can either be plus or minus. And sometimes we really have to like do some detective work to figure out, should I put that as a plus or minus in my equation? And that's the hardest part of this equation. So I'm going to go over this diagram and show you the way that you can think of it. So let's just consider Q first. It's a lot simpler. So if Q, or heat, enters a system, we said that the system is gaining heat, and we want to think of it in terms of the system. So because the system's gaining heat, we give that Q value a positive value. Okay. On the other hand, if the system loses heat, heat is being lost by the system, I can draw an arrow leaving the system. Because the system is losing heat, I'm going to put a negative sign. Okay. Now, work often confuses students, but you can think of it in a very, very similar way. So just like how we thought of when Q was entering a system and we drew an arrow into the system, you can do a similar thing for when work is being done on the system. So if the question says the work is being done on the system, think of it as you can draw an arrow going into the system. The work's being done on the system. And so just like how when Q was going into the system, it was positive, it's the same for work. Okay, now on the other hand, if it says the system is doing the work, work is being done by the system is doing the work, we can draw an arrow going away from the system. And just like how when we drew an arrow going away from the system for heat and it had a negative sign since heat was being released, when work is being done by the system, we give that work a negative sign. And we'll see an example of applying this soon. Okay, this is just summarizing exactly what we just went over. One more equation that I'll introduce to you guys quickly. I think we're going to go over probably around 5 minutes, so just stick with me. But one other equation that we'll introduce here is how to calculate for work. So This equation is how to calculate internal energy, and now we're looking at how to calculate work. So the equation for work, the main equation that we'll see, is work is equal to negative P delta V, where P is just some constant pressure that you'll be told in kilopascals, and your delta V is the change in volume. So just remember that anytime you have delta of some variable, you take the final volume and you subtract the initial volume. So you want to take final minus initial, and we're going to have volume in liters, and that's going to allow you to solve for work in joules. Okay? So let's actually try this question. I'll give you guys a minute to try this one or so to think about how you would solve for this. It's a good question. Okay, I'm going to start taking it up. If you want to keep thinking about it, go ahead. So what I'll do is I'll first just write out variables we know. Okay, so we have 20 liters of an ideal gas expands to 40 liters. Okay, those are both volumes. And there's a constant external pressure of 1 atm. And then it also tells us that there's this much energy being absorbed by the reaction, and it wants to know what is the change in internal energy. So because I'm being asked for the change in internal energy, I'll want to remind myself of what that change in internal energy equation was, where it's Q plus W. Okay, great. So I need to pretty much solve for internal energy. I need Q and I need W. Okay, so I'm going to just stop the polling for this. Let's just pause for a second. So the Q, it looks, I would have to know how much energy is being absorbed or released. And so here it actually tells me that energy is being absorbed. So that's actually going to be my Q. So do you think Q should be positive or negative? So vote A or B just for that part. Okay, so this question we agree on. That's good. Okay, most of us agree. So let's make sure the other people agree too. Okay, so here, because it's saying that much energy is absorbed by the reaction, that is saying the system absorbs energy. So if we go back and look at our picture, if the system absorbs energy, we have an arrow going into the system, we're going to put a plus sign. The system is absorbing or gaining energy. We give it a plus sign for that. Okay, so now we know the Q should be a plus sign. So Q is going to be plus 2.2 kilojoules. Okay, and then next thing we have to do is figure out how can we solve for work. So I see that I have a pressure and I have volumes. Okay, so I know the equation for work is negative P delta V. Okay, now this was a little tricky where here I said to make sure the pressures are in kilopascals. Okay, but here the pressure they gave was actually an ATM. So to convert them, 1 ATM is just equal to 101.3 kilopascals. Okay, so here you're going to want to make sure you plug your pressure in kilopascals. And now for the volume, it's just the final volume minus the initial volume. So it says 20 liters of an ideal gas expands to 40 liters. So this is your initial volume, and the 40 liters is the final volume you get after expansion. So now your delta V is your final volume minus your initial volume. So you're going to do 40 liters minus 20 liters. It's a little bit of a tricky question. So then we're going to be able to solve for work, and you're going to get negative 2026.5, and we said the unit of work that we would get is joules. So this is another step that a lot of students would probably forget on their test, where remember that the units of work we get are joules, but the units of Q they gave us are kilojoules. So we need to convert that into joules. So just multiply by 1,000 and you would get 2,200 joules for Q. And then you would put the work sign, it's negative, so you're adding a negative value for work. Okay, and now you're going to be solving for delta E. So it's 173.5. So a bit of a tricky question, but that's your answer. So the answer was C here. I can go over the details of why there's a negative in that equation at the end of the session, okay? But let me just keep going through this, and I'll make sure to come back to that at the end. So, yeah, now we first figured out what variables we had. We figured out the sign of Q, and then we solved for work, remembering to use correct units, and then we just plugged everything in and making sure that it was both of them were in joules, so we could add that together. Okay, the last little note I have for you is that we mentioned already the equation for work is negative P delta V. And there's another equation for work that's not as commonly used, but I'll just touch on that quickly. And we can actually, if you remember the ideal gas law, PV is equal to nRT. This PV looks pretty similar to that. So what I'll do to make it even more similar is just add this delta V there. Since I add it on the left side, I'll also add it to the right side of the ideal gas law equation. And then instead of this P delta V, I'm going to plug in nRT for that P delta V. So you get a new equation for work. That is work is equal to negative delta nRT. And again, for the most part, you're going to use this first equation. This one is a lot more common. But some problems are not going to give you a pressure and a change in volume. And so if you're asked to solve for work, then you're going to be like, how do I do that without a pressure and a volume? And so in those cases, you're going to be able to use the second equation, where R is just your gas constant that we've seen many times. You're going to use 8.314. T is the temperature in Kelvin. And delta N is a little confusing, so don't forget this, but it's moles of gas on the product side minus moles of gas on the reactant side. So you're just interested in moles of gas. Okay, so the delta symbol is just for the delta N, change in the number of moles of gas. Okay, so let's just do this last example together. And does the following reaction involve pressure, volume, work? So if you see that first, you're like, okay, this is asking me about work. I know how to do this. You're thinking, okay, I know an equation for work. It's negative P delta V. And then you realize, okay, wait a second, there's no pressure, there's no volume here. So I definitely can't be using that equation here. So then you remember, okay, there's another equation we can use that's negative delta nRT that we just saw over here. Okay, so we just took delta nRT instead of PV, and we get this new equation. And so here I still don't have a value for R, and I still don't have a value for T. But because I'm given a balanced chemical reaction, I can see if there is a change in the moles of gas. And if there is some number there for the change in the moles of gas, then R is 8.314, and the temperature is just some number, right? We don't have to know exactly. Then either what we do have to know is that as long as there's some number for delta N, you're going to get some amount of work. So here it's just asking, does this reaction involve work? It's not asking how much. So if we have a value for delta N, we'll have work. So what do you guys think? Let's vote. Okay, so let's see. So does it involve work? So I know that if there's a change in the moles of gas, then it will involve work. So on the left side, I have 1 moles of gas, since the coefficient is just 1, plus 2 moles of gas. So you have in total 3 moles of gas. And on the right side, I just have 1 moles of gas. So if I actually wanted to calculate delta N, I can show you how you would do that. So you would take the moles of gas on the product side. So 1 minus the moles of gas on the reactant side, 3. So 1 minus 3 is -2. All that matters is you have some value for delta N. It's not 0. And so because you have some number, then there is a possibility, then this reaction does involve work. And so that's why the answer was A for yes. Okay, so the session is done. If you guys had an extra couple questions, I can stay on a little longer. And don't forget, next week's session, we're going to go over the rest of thermochemistry, part 2 and part 3. Okay, so I hope you guys found that helpful, and I look forward to seeing you guys next week. Okay, so a couple questions here. How did you get delta N? So delta N is moles of gas on the product side. So it's interested in delta N is your delta N final for gas. So moles of gas on the product side minus moles of gas on the reactant side. No problem, you guys. I'm glad you found it helpful. You won't get the annotated notes, unfortunately, for the session, but I did put together a solutions booklet. So any of the problems we went through, if you're like, I'm not sure if I completely wrote that properly, you can check the solutions booklet. It has full solutions to all of the practice questions we did today. Did you get the 1 in products? So for this equation, I got 1 in products by just looking at this coefficient. So there's a gas here, and there was 1, a coefficient of 1 there. So there's 1 mole of gas. Whereas on the reactant side, we did 1, a coefficient of 1 there, plus this 2 to get 3 moles. No problem, you guys. I'm happy you liked it. Okay, so someone wants to see page 15 quickly, and then I'll go through the last question that somebody had about the work equation. So that's all I had for page 15. Page 11 we'll do quickly. Okay. The next week is free as well. I should have mentioned that. My bad. Yes, next week's free as well. It'll be mentioned again in the emails. Okay, so no problem. So quick question about rate of effusion here. How did I know what to put on the top or what to put on the bottom? So it actually doesn't matter which one you put on the top or the bottom. So you would get the same answer if you put the rate of effusion of the light on the top and then the rate of effusion of dark on the bottom. But then just remember that whichever order you choose, so in this case, I put dark on the top, the root mean squared speed of dark on the top. So make sure you put its molar mass in the bottom. But no matter what you do, you're still going to get this end equation at the end, which tells you how their molar masses were related. So that's like the main part we needed for the answer. But whether you choose this dark or light, you could have flipped that. It doesn't matter. Okay, the last question. Why is there, okay, that's a good question. It's a little complicated, like you don't have to understand the details, but pretty much if I had let's say my volume is 10 liters in scenario 1. In scenario 2, I expand my container and I now have 20 liters, right? What's the delta V here? So in this scenario, our delta V is the final volume minus the initial volume. So 20 minus 10, and you get a delta V of 10 liters, positive 10 liters. Okay, so your delta V is positive, but what did we say about when, so in this example, to better show this, there would be like a piston here and gas particles in here. And what would happen is the gas particles would push on that to create a larger volume. And so here, the gas is acting as the system, right? And the system is pushing and doing the work to expand this container. And so if the work is being done by the system, right? The system is pushing, the system is doing the work. You think of it as an arrow going away from the system. And so work is negative, okay? And that's why we have to put a negative sign here, because I need my work to be negative when my delta V is positive. So in this example we just saw, delta V was positive, right? Plus the volume, delta V was plus. But the work, we actually want to get an end value of work that is negative, because the work is being done by the system. Okay, so that's why that negative sign is there. Okay, so thank you guys so much for attending. I'll see you guys next week. And I wish you guys the best of luck and everything. Good vibes, positive vibes to you guys in this time. And yeah, if you guys have any ideas for me to take up in weekly sessions, or have ideas of how to improve these, I'll definitely take your feedback. If you ever want to add more feedback or you have additional questions, here's my email too, which I will share in the beginning of next week's session. Okay, Avneet@wizeprep.com. Okay, so I'll see you guys. Thank you guys so much for attending. And next week is free. Okay, so don't forget about it. Same time next week. Bye.